Okay, good day. So let's consider additional sample problems for simple strain under statically indeterminate members. So for this problem, so this is modified problem number 245 in page 53 of the 4th edition book. So the composite bar is firmly attached to unyielding supports. So compute the stress in each material caused by the application of the axial load, that is P equal to 50 kips. So we have two materials, aluminum and steel. So we are given as well the corresponding lengths, area, as well as the value of the bulk modulus of elasticity. So the given and the requirements are summarized at the left side of our screen. So for the solution, so let us consider first the equilibrium aspect. So for the equilibrium, if we will now consider the reaction at both ends of our compound material, so we will be having the reaction at the left end, and we have as well the reaction at the right end. So if we will now consider the summation of forces horizontal equal to 0, that is to the right, minus to the left forces are equal to 0. So to the right, we will consider P, while we have to the left both reaction at the left and reaction at the right. Therefore, P minus R sub L minus R sub R is equal to 0. So if we will now rearrange our equation, we will come up with the equation that is P equal to R sub L plus R sub R, that is equal to 50 kips. But, so if we will now cut the section that is at the aluminum side for us to expose now the internal reaction, so we will now expose our P sub A, or the internal reaction for the aluminum material. On the other hand, if we will cut section through our steel material, then we can expose as well the internal reaction under the steel material. So if we will now consider these conditions, we will come up with our relationship, that is the RL is equal to P sub A, as well as for the reaction at the right is equal to P sub S. Therefore, updating our equation, we have now our P sub A plus P sub S is equal to 50 kips. Our working equation number 1. So set aside our equation. Next, let's consider the compatibility, or otherwise the deformation equation or relationship. So for the deformation now, if we will consider the original condition of our material, and due to the application of this P, that is 50 kips, so the tendency is for the aluminum, it will elongate, while for the case of the steel, it will now compress, or otherwise it will shorten. So with this difference in length now, we can consider that for our the highlighted portion, so for our delta S, so that is for the shortening of our steel material, while for the red portion, or the highlighted in red, is the elongation for our aluminum material. Therefore, if the elongation is the same as the shortening, thus for our delta S, it is equal to our delta A. So if we will now substitute the equation for the deformation delta, that is equal to PL all over AE, we will now update our equation, that is for the left side, for the steel, that is PS LS all over ASES, while for the right side, we have P sub A LA divided by A sub A times EA. So if we will now substitute the different data, we have PS times the length of the steel material, which is 12 inches, divided by the area of that steel material, which is 2 square inch, then times the value of ES, which is 29 times 10 raised to 6 PSI. So it is equal to, for the case of aluminum, we have P sub A, multiply that with its length, that is 15 inches, divided by the area of the aluminum, which is 1.25 square inch, then multiply with E, that is 10 times 10 raised to 6 psi. So we can already cancel out the unit of the length as well as the unit of the area. And lastly, for the E, we can cancel out both the times 10 raised to 6 and psi. And if we will cross multiply everything, so the 12 as well as the 2 and 29, we can update our equation as PS is equal to PA times 15, then times the cross multiplied value, which is 2, and multiply that as well with 29. So divided by the cross multiplied 12 with 1.25 and 10, leaving us the relationship of PS as equal to 5.8 of P sub A. This is our working formula number 2. So again, set aside our equation number 2. So for this value of PS in terms of PA, we will then substitute it in equation number 1. Updating now equation number 1 as PA plus 5.8 PA equal to 50 kips. Therefore, we can already determine the value of PA from this equation as 7.353 kips. Knowing the value of PA, then let us substitute this in equation number 2 for us to obtain the value of our P sub S, wherein P sub S is equal to 5.8 times the working value of PA, which is 7.353 kips. Thus, for PS, or the force or internal reaction for the steel, it is 42.647 kips. So for the stresses, for our sigma A, it is equal now to PA divided by A sub A, wherein PA is 7.353 kips all over the area, that is 1.25 square inch. So from this, we will come up with the value of our sigma A, that is 5.882 KSI, and take note that for the aluminum, it elongated, therefore it is under tension. While for the case of the steel material, it is equal to PS all over AS, that is for PS 42.647 kips divided by the value of the area, which is 2 square inches. Updating this, we will come up with sigma S as 21.324 KSI, and again for the steel material, it shortened, therefore this is under compression. So for our next example, so we will consider problem 254 in page 55 of the 4th edition book. So for the problem, the rigid bar of negligible weight is pinned at O or point O and attached to 2 vertical rods. So assuming that the rods were initially stress-free, so what is the largest load P that can be applied without exceeding stresses of 150 megapascal in the steel and 70 megapascal in the bronze rod? So for this 150 and 70, these are the allowable or the maximum values of the stresses for both steel and bronze rod. So the summary of our given as well as our sole requirement, that is Pmax, are specified at the left side of the screen. So for our solution again, so for the first process, we will consider the equilibrium side of our analysis. So for the equilibrium side, if we will now try to expose everything under our free body diagram, so at point O, since the support is a hinge, therefore we have 2 reactions. So 2 actual reactions, one of which is horizontal while the other one is vertical. Next, if we will cut now the rod at the steel, or if we will cut the steel rod, then we will expose our reaction for the steel. Typically, if we will apply that pulling force P, therefore our steel material is under tension. While for the bronze, if we will now expose its internal reaction, so actual reaction, it is the same as the steel, so it will undergo or underwent tensile force and tensile stress. So from this alone, So we have 4 different unknowns, namely OH, OV, PS, and PB. So we are only interested with PS and PB. Therefore, we need to eliminate the reactions at our hinge support. So in doing that, we need to sum moment at that point O. So that is now equal to 0. Therefore, the clockwise moments minus the counterclockwise moments is equal to 0. So let's take first our first value, which is the unknown P. So for the unknown P, the reaction of this P with respect to point O is counterclockwise. Therefore, for counterclockwise, that will be a negative value. So negative P times its lever arm. So from P towards point O, it is 2 meters. Next, let's take now our moment with respect to that force for the steel rod. So for PS now, the rotation of this load with respect to point O is clockwise. Therefore, it will consider a sign that is positive. So positive P sub S, then multiply that with its perpendicular lever arm towards point O, that is 1.5 meter. And similarly for our PB, it will have the same rotation as PS, that is clockwise, which means that it is positive. So positive PB times the lever arm. So from point B or point of the bronze towards point O, that is 1.5 plus 1.5, or that is 3 meters. So we do not have additional loading or moment. Therefore, this be equated to 0. So we will then cancel out the units of the length measurement. And updating our equation, we have now 2P is equal to 1.5 of our P sub S, then plus 3 of our P sub B. So if we will cross multiply this factor of our P, that is 2, we will have the updated equation for P, or otherwise our P max later on, that is 1.5 of PS plus thrice of PB divided by 2, our first equation. So set aside our first equation. Next, let us consider the concept for our compatibility side, that is for our deformation equations. So again, from our original diagram, so if we will already apply this value of P, what will happen to our material? Taking that for the bar material, this is rigid. Therefore, by just applying this P, so this bar will rotate, and for our rod, this will elongate, similar to this one. Okay, so for our elongations, so we will be having elongation for the steel, that is again in reference to its original line, as well as for the elongation of the bronze material. So for the analysis for the deformation, so we can analyze this by means of similar triangles or by means of ratio and proportion. So let's take first for the side of the steel material or steel rod. So if we will now take this as our sample working triangle, so the orange triangle, then if our ratio be in a form of the height all over the base, then for the first ratio, that will be our deformation for the steel or delta S divided by its base, which is 1.5 meter. On the other hand, for the next similar triangle, if we will now be noting this green triangle for the case of the bronze, so we will now consider the height, that is for the deformation of the bronze, divided by the total base, which is twice of 1.5 or otherwise 3 meters. So if we will cross multiply 1.5 meter towards the delta B, we can already update our equation for the delta S as equal to delta B times 1.5 meter divided by 3 meters. And 1.5 divided by 3 is otherwise 1/2. So therefore, our delta S is 1/2 of delta B. So if we will now substitute for our equation of our delta, that is again PL all over AB, then for the steel, we have now PS LS all over ASES is equal now to 1/2 times for our bronze, that is PBLB all over ABEB. So updating now our given, so we will come up with our equation, that is PS times the length of the steel material, which is 1.5, divided by the area of the steel material, which is 900 square millimeters, and further multiply this with ES, that is 200 gigapascals. So it is equated to, we have PB times the length of that bronze material, which is 2 meters, divided by 2 times the area of that bronze material, which is 300 square millimeters, and multiply that with E, which is 83 gigapascals. So cancel out again for the unit of the length, unit for the area, as well as the unit for E, that is the gigapascal. And cross multiply all the factors of PS, so for numerator and the denominator. Updating now our relationship, as for our PS, it is equal to PB with the factor that is 2 times the cross multiplied values, which are 900 and 200. So divided by 2, then multiply that with our factor that is 1.5, then times the values of the area, that is 300, and E, which is 83. Thus, for our final relationship, we have PS is equal to 400 all over 83 of our P sub B, our working equation number 2. So for our next process, so since by means of inspection, we have 3 unknowns and only 2 equations. So therefore, for us to come up with the value of our P maximum, we need to check our given, in which for the given, we are provided with the working, the allowable, or the maximum values for both steel and bronze material. Therefore, let's check the stresses. So in checking now for the stresses, let us consider first the maximum for the steel material, in which for the maximum for the steel material, it is equal to 150 megapascal, that is equal to the force all over its area. Thus, if we will cross multiply the area, we will come up with our value for the force for the steel, that is 150 newtons per square millimeter. Multiply that with the area of the steel bar, which is 900, or steel rod, 900 square millimeters. So cancel out the unit for the area, leaving us PS as 135,000 newtons. So knowing this initial value of PS, let us substitute this in equation number 2 for us to obtain the value of our PB. So for PB, it is equal now to 83 divided by 400 times the PS value, which is 135,000 newtons. For PB now, the value is 28,012.5 newtons. So knowing this initial value of PB, then let's check the value of its stress and compare to the maximum value of that stress for the rod material. So for the stress for the bronze, the sigma B is equal to the force all over the area, wherein the force is 28,012.5 newtons divided by the area of the bronze, that is 300 square millimeters. Thus, the value of the stress is 93.375 megapascals. But the thing is, we need to compare this with our sigma B, working, allowable, and maximum. So the value of that maximum is 70 megapascals, which means that the value of sigma B, that is 93.375 megapascals, is greater than 70 megapascals, which means that for these values of PS and PB, it is unsafe or otherwise not applicable. Therefore, for our analysis, what if we will consider bronze instead of the steel? So considering now the maximum for the bronze, so for our sigma B, the maximum is 70 megapascals. That will be equated to the force all over its working area. Cross multiply the area, we have now the value of the force that is 70 newtons per square millimeter. Multiply that with the area of the bronze, that is 300 square millimeters. Cancel out the area. We have now PB as 21,000 newtons. Now, knowing PB, then substitute in equation number 2 for us to obtain the value of PS, wherein PS is equal to 400 divided by 83 times this PB, that is 21,000 newtons. Thus, for the value of PS, it is about 101,204.819 newtons. Knowing this PS, let us check the stress for the steel rod. So for the stress, it is equal to the force all over the area, wherein the force is 101,204.819 newtons divided by the area, that is 900 square millimeters for the steel material. Therefore, for the stress for the steel, using this value of force, it is about 112.45 megapascals. Comparing this with the maximum possible stress for the steel material, that is 150 megapascals, this value, that is 112.45, is far less than 150 megapascals, which means that for this value, it is safe. So knowing that safe for both bronze and steel, then it is safe for us to adapt the values of PB as well as for our PS. So for PB, the value is 21,000 newtons, while for PS, that is 101,204.819 newtons. Now, for us to determine the value of the maximum P, so we have already the values of our PB and PS. Therefore, let us substitute these values in our working equation number 1. So for our P max under equation number 1, it is equal now to 1.5 times the value of PS, that is 101,204.819 newtons, then plus 3 times the value of our PB rather, that is 21,000 newtons. So this be divided with 2. Therefore, for our final answer, for the P maximum, it is either 107,403.615 newtons, or dividing this with 1,000, we will come up with the value that is 107.404 kilo newtons. Okay, so that's it for our sample problems for the simple strain under statically indeterminate members. So take care and God bless.